So in this video, we're going to look at circuits with an inductor and a capacitor, or LC circuits. And this is in chapter 33.5 of the textbook. Okay, so imagine, if you will, we're going to create a circuit. We're going to attach a capacitor and an inductor, and just so something interesting will happen, we're going to assume that the capacitor is going to be initially charged. So the capacitor has some charge on it. And again, to simplify things, we're just going to assume that there's no resistance anywhere. Okay, so the energy in this circuit is going to oscillate or go back and forth between being in the capacitor and the inductor. And we can see what's going to happen. So we start here. So we've got our capacitor, we've got our inductor. So you close the switch. Well, initially there's no current, and the capacitor we decided is going to be charged up. So what's going to happen then is, well, the capacitor is going to start to discharge. And that's going to generate a current, but an increasing current. But when the current is changing, then we're going to induce a EMF in the inductor. So initially we had all our energy was stored in the capacitor, but then as the capacitor is discharging, now we've got some energy in the capacitor in the electric field, and in the inductor, the magnetic field. So eventually the capacitor is completely discharged, right? And at that point the current is a maximum, and so then we've got all of the energy is stored in the inductor, in the magnetic field. But now we have nothing driving the current anymore, so the current is actually going to start to decrease again. And well, it's going to go in the opposite direction. Right, because that's the flux through the inductor decreases, so then that's going to induce an EMF and we're going to get a current again. So at this point, right, so now the capacitor starts to charge up again, and we're sharing the energy between the inductor, the magnetic field, and the capacitor, the electric field, until eventually the capacitor is fully charged, and at that point, well, the current is going to be zero, so we've got no current and no changing current, so there's no induced EMF in the inductor, so once again everything is stored in the electric field in the capacitor. And this is just going to continue, right? So just notice that the current here is actually opposite to the current we started from, so eventually the process is going to repeat and we get this current. You can imagine, or if you think in terms of the energy is just kind of sloshing back and forth between the capacitor and the inductor. So the charge, so we can actually solve for the charge on the capacitor. It's going to be varying, so it's going to be some cosine function. And the frequency that it's varying at, omega, the angular frequency, is going to be the square root of 1 over the self-inductance times the capacitance. And well, if we know Q of t, then we take the time derivative, that gives us I of t, so the derivative of cosine is going to give us a sine. And the frequency is the same, and the maximum current is just going to be omega times Q max. So then the energy versus time is going to look something like this. So the green is the energy stored in the inductor, the purple is the energy stored in the capacitor. So the total energy, well, we can write it as the maximum charge squared over twice the capacitance, or we could write it as 1/2 L times I squared max.